And yeah, so thanks to the organizers for inviting me. Super happy to be here. So in my presentation, the next half an hour, I'll be talking about the quantum advantage in learning how to use entanglement to learn a physical process much more efficiently than if you did not use entanglement. So this is what I'll be talking about. So let's get started. Oh, that's the wrong way. All right, so there has been a race in demonstrating quantum advantage, quantum supremacy in the various different systems, very different platforms. It has been demonstrated in superconducting platforms a couple of times, and there's also been a strong race in demonstrating this in an optical setting. I mean, on a photonic platform. And these are two of the milestone papers where Gaussian boson sampling were demonstrated and quantum advantage was claimed. So in the first experiment by USTC from China, they produced 50 squeezed modes injected into a Gaussian linear network and did photon counting at the output. I mean, demonstrating Gaussian boson sampling and claimed to have shown a quantum advantage. And the same was done by Xanadu in Toronto in Canada. So they made, I think it was 250 mode, a Gaussian boson sampler using time multiplexing techniques and also claimed to have demonstrated quantum advantage. These claims have been contested and also it's not really known how many modes is needed, how much squeezing is needed, and how much loss can be tolerated in order to demonstrate quantum advantage. So we do have an experiment where we're trying to demonstrate quantum advantages in also in Gaussian boson sampling, where we're trying to scale this to thousands of modes, and then hopefully we'll be demonstrating the quantum advantage. But that's not what I'm going to talk about in my presentation. I'll be talking about the demonstration of quantum advantage in learning a physical system. So not quantum computational advantage, but quantum learning advantage. And what do I mean by quantum learning? So the idea is to learn about a physical system. And how do we learn about a physical system? I mean, we do this on an everyday basis in the laboratory. So we start by preparing a set of pulses, optical pulses. We shine this onto our physical system that we want to learn about. We might have some scattered light, or our pulses will be changed, and then we perform measurements. It can be homodyne measurement, it can be photon counting measurements, and we get data out. And with those data, we use a lot of sometimes very heavy post-processing to learn about the process. And we can then extract information about some statistical properties, the mean value, the variance, or higher order moments, or some probability distribution. So this is like the standard way of learning about a system. So what we mean by quantum enhanced learning is that the setup is similar. So we start by preparing some quantum states of light. So now it can be maybe a bit more advanced states of light, entangled states of light. And then we also shine this onto the physical system. And then before we do the actual projection of the measurement and extract the classical numbers, we do some quantum processing to optimize our estimate. So we do some quantum processing before we do the actual measurement, and then we also do some statistical estimates. So this is what we mean by quantum enhanced learning. And then the question is that I will be posing in this talk is that can we beat the classical approach, the conventional approach, by using a quantum approach? So, I mean, this is just one example of learning about a physical system, something that is done quite often in many labs. For example, Raman spectroscopy, you want to learn about the mechanical vibrational spectrum of molecules. So you shine light onto the molecules, and then you reflect light onto a detector, and then you look for displacements of the light beam, changes in the amplitude and phase quadrature of the light beam, and that gives us information. I mean, through some classical processing, it gives us information of the vibrational spectrum of molecules. So the question is, I mean, can we do this better by replacing this detector with maybe a quantum processor, and also replacing the laser with something more sophisticated, some non-classical state of light? This is what this could be one example of quantum enhanced learning of a practical problem. Okay, But let's jump back to theory and look at maybe a bit more impractical learning scenario. So here, what we are looking at now is, and that's also what I'll be talking about the rest of my talk, namely the learning of a random displacement channel. So again, the idea is to prepare some states of light, shine this through a channel, and in the channel, the light field will experience a random displacement in phase space. So displacement in the amplitude and displacement in the phase. So completely random displacement in phase space as shown here with a size alpha that is random. Okay, and now we assume that we have n channels, not only one but n channels. So it could be like n different fibers that we send light through, and the light will then pick up noise or random displacement in those n channels. And it can be very complicated noise because it can also be correlated across all channels. So these channels are not independent; they could be correlated. And then we try to extract information by doing measurements at the output of the channel. So this is basically the random displacement channel that we're considering. So we have a displacement of the input beam. The input beam is rho. We have a displacement, and this displacement is random over this distribution here, this probability distribution P of alpha. And now the idea is basically to learn the probability distribution. This is what we want to do. We want to learn the probability distribution of this random displacement channel, which, remember, is in n dimension, or we have n modes. Okay, or similarly, we want to learn the characteristic function of that channel. The characteristic function is just the Fourier transform of the probability distribution. So we want to learn the characteristic function. So one example of a probability distribution is what you see here for one mode channel. So these are x and p. Random displacement, so it is an oscillating probability distribution in this case here that we want to learn. And what is the Fourier transform of this? This is indeed the characteristic function that you see here, and where you see some blobs here for larger beta values. So beta is the frequency of the probability function, or the oscillation in the probability function. Okay. So this is what we want to do. We basically want to learn the properties of that channel. So now, instead of learning the properties of n spatially separated channels, we want to learn n different segments in time. So we could say that we're now learning a displacement process rather than learning displacement channels. But the idea is exactly the same. The reason that we jump to this time degree of freedom instead of the spatial degree of freedom is that it's much easier to implement experimentally, as I'll get back to later. But it's all the same. Okay. All right. So how do we learn this? So of course, we can use a classical strategy, and the classical strategy is to start out with preparing some non-entangled states. And the most obvious thing to prepare is like a vacuum state or a coherent state of light. That's what we often do in the laboratory when we're going to learn about a certain process. So this is what we'll do. So we will be preparing a vacuum state, and this vacuum state is then randomly displaced in phase space as a result of the noise, or as a result of the impact of the channel. And then, in order to learn information about this displacement, we will have to measure conjugated quadratures, amplitude and phase quadratures, and the way to do this is to use a heterodyne detector. So, and we also know that when we perform heterodyne detection, then there is a noise penalty because we're trying to extract information about conjugated quadratures. So we have actually an extra noise contribution through the measurement. So we have noise in the input from the vacuum state, and then we have an extra noise contribution from the actual measurement. Because the x and p are incompatible variables. So you can see that you're simply blurring out the resolution in phase space, and therefore it seems obvious that you need to conduct a lot of measurement. You have to repeat the measurement many times in order to get a good resolution of estimating the characteristic function. So now we assume that we perform measurements. We perform capital N measurements, and we get an estimate that I call the lambda tilde. This is my estimate after performing capital N measurement. I assume that I want to have a precision that is less than what I call epsilon. So it's just a difference between the estimate and the real value of the characteristic function, and I want to have this with a success rate of 1 minus delta. The delta is the failure probability. And then using the Hofting bound, I can then find the number of experiments that is required to get this precision with this success rate. The very simple calculations. This is simply the number or the complexity or the number of experiments I need to conduct, n, capital N. And we see, yes, of course, it's a function of the precision and it's a function of the success rate, but it's also a function of this beta factor here. So remember, this is the parameter of the characteristic function, which is associated with the frequency, oscillation frequency as a probability distribution. So if this, and we see that the number of experiment goes with the exponential to this parameter beta. So that means that the larger the beta, the more number or the more experiments you need to conduct in order to get a certain precision. So it scales exponentially with this number. Beta is also linearly proportional to the number of modes. So that means that the number of experiment requires actually scales exponentially to the number of modes that we want to probe. Okay, so now let's look at our quantum strategy. So here the idea is to instead of preparing classical state or vacuum state, coherent state, we decide to prepare EPR states or entangled two-mode squeezing state. So where one of them is the probe and the other mode is like a memory node. So we send the probe through the channel while memorizing the other mode, and then we did an entangled measurement or a joint measurement or Bell measurement at the output. So remember, this was the resolution in phase space that we encountered using vacuum state or coherent states. But now, because we're using two-mode squeezing and we're performing joint measurements, and in joint measurement we're measuring the sum of the amplitude quadratures of the two-mode squeeze states and the difference of the amplitude quadratures, and these are compatible variables. That means that we can extract information of these two variables simultaneously without any noise penalty if we have a lot of entanglement or a lot of two-mode squeezing. So that means that the phase space resolution would look like this. We simply shrink the noise both in amplitude and in phase quadrature simultaneously by using a two-mode squeezing. And then we can also find the number of experiments, the sample complexity that is required required when you're using a two-mode squeeze state and a joint measurement. Then you see that it goes also as an exponential function as we saw before. It's almost identical to what we saw before, but there's of course a main difference. A key difference is that we also now have this factor here, e to the minus 2r, where r is the amount of squeezing or the amount of entanglement in our two-mode squeeze state. So if r is 0, then there's no entanglement, then we're back to the original results. But if r goes to infinity, I mean, then we have a lot of entanglement, and if r goes to infinity, then this exponential factor here goes to 0, or it goes to 1. So it is killed. So we simply kill the exponential scaling just by using such a simple system of two-mode squeezed vacuum state or EPR states and joint measurement. And joint measurement was just a beam splitter and two homodiene detectors. So we can simply either we can completely kill the exponential scaling, or we can reduce the impact of the exponential scaling. So this sounds interesting. So therefore, we went to the laboratory and tested the experiment. So and the experiment is not too difficult, because I mean we have the different modes at different time segments, not different spatial modes, but at different time segments. So therefore, we could just produce the two-mode squeeze states at different time segments. So it's a time multiplexed experiment. And for this, we used two optical parametric oscillators, two single-mode squeezers, and interfered them on a 50-50 beam splitter to produce entanglement. So we used those rather bulky systems. So we're still using a big bulky system for our squeezer, although we're also trying to migrate into photonic integrated circuits. It's not working that well yet, but so the good old big bulky systems are still those that gives most squeezing. So we produce about 10 dB of 2-mode squeezing from these single mode or 2-mode squeezes. So they have very high escape efficiency. That means that we don't lose much of the squeeze light when produce them inside the cavity. Bandwidth is fairly small, 25 megahertz, so we're not producing it that fast. But it's quite nice. It's operating at the telecom wavelength. And although we're producing 10 dB of squeezing, we are losing a lot of the squeezing on the way. So we actually only used or measured 5 dB of squeezing at the end of the experiment. Okay. And then because it's a time multiplex experiment, we have to separate the squeezing at different time segments. And this we did using pulses at a certain sideband at 3 megahertz, and the length of the pulses were around 1 microsecond. Okay, and we implemented the channel, which is done exactly here. And this was implemented using a pair of modulators, an amplitude and a phase modulator, that was then modulating one mode of the 2-mode squeezed state. And this was then controlled by a computer, so we are implementing a certain displacement pattern. Okay, and then what we did was that we performed the Bell measurement, homodynamic measurement, or we mixed the 2-mode squeeze state on a 50-50 beam splitter. We did the amplitude quadrature measurement in one output port that gives us one number, and phase quadrature measurement of the other output port that gave us a second number. And then we added the numbers and came up with this complex number for every single pulse. And this was then used to yield an estimate of the characteristic function given by this expression here. So whenever we have one measurement, x and p, we form this number key, complex number, which we then plugged into this formula here to get an estimate of the characteristic function. All right, and now having this estimate, and we of course we know the displacement that we have put onto the beam, then we could find the precision. I mean, we could take the difference between the two and then find the precision, and then repeat the experiment as many times as we want. Okay, so this is just some of the experiments, some of the results that are now presenting. So this is the true characteristic function. This is the one that we imposed onto our light field. And here we consider just 16 modes. And this was, I mean, it's a high dimensional space when we have 16 modes. So we just look at one cut through that 16 dimensional space. And this was basically the characteristic function that we were imposing onto our light field. We did the measurement, but first we did it without the entanglement, using the standard conventional classical strategy. And we did this using about the 200 trials. I mean, we repeated the experiment 200 times, and then we got this red curve. This was our estimate, and we can see that for low beta value, we can estimate our characteristic function pretty well. But when the beta value becomes large, when we're going to resolve the fine details of the phase space, we get a problem. It simply just explodes. So the difference between the true value and the estimated value is poor. And now we can, of course, repeat the number of experiments. And now we do the experiment 5,000 times, and then we can see the estimate becomes better. And for 10,000, 100,000 times, it becomes even better. So the more time we repeat the experiment, the better is the estimate. That makes good sense. But this was only for 16 modes. So now if we increase this to 30 modes, then it's of course much harder. So now we actually set the number of experiments to 100,000. And now instead of increasing the number of experiments, we simply added squeezing, or 2-mode squeezing. So, okay, so first we did not have any squeezing, so just use the coherent state or vacuum state for its reconstruction, and we do fairly good reconstruction up to this point, then it just explodes. And now we use a 2-mode squeezing of 2.3 dB. You can see now we do a bit better. And if we have 5 dB of 2-mode squeezing, yeah, then we do much better. So we can see that by using entanglement, by using squeezing, we can do better and better. But still, for 30 modes, I mean, we can still do it the classical way. We can increase this number of repetition to maybe 1 million or 10 million. This we can still do classically, and then we can resolve the features. But what happens if we go to even more modes? So of course we increased the complexity by increasing the number of modes. And this is what we have done here. So this is the sample complexity or the number of experiments that is required to get this precision with this success probability. And first we did this using the conventional approach without two-mode squeezing, and then we got the red line here, where the dots here correspond to experimental results. So here we went from 0 modes all the way up to around 30 modes. And then after 30 modes, I mean, it was actually difficult to repeat. I mean, at this point, we were already at almost the 10 million repetitions of the experiment. It just took too long to repeat or to estimate the true value of the characteristic function. So now we turned on our two-mode squeezer and our Bell measurement, and we tried 2 different squeezing degrees, 2.3 and 5 dB. So let's just look at the 5 dB squeezing entanglement source. And in that case, we could actually keep repeating the experiment all the way up to 100 mode. And still only using around 100,000 trials. So we saw a huge and a significant improvement by using just 5 dB of two-mode squeezing. So an improvement of 11 orders of magnitude. So there's 11 orders of magnitude from this two-mode squeeze state probe to the vacuum probe up in the top. Okay, and you could also turn this into numbers. So it took 15 minutes to do this measurement, assuming a bandwidth of 1 megahertz. Whereas if we were to do the other one, then it would have taken 20 million years to reach the same precision using a vacuum state and a conventional measurement approach. So it's a huge advantage using two-mode squeezing. Okay, so I should point out the main people of this work here. So the theory was done in tight collaboration with the group of John Prisco and Liang Jiang, and the experimental work was done by a number of people, but the lead authors were Cheng Hao and Roman. I should also point out that we were not the first to demonstrate quantum learning. It has been demonstrated on a superconducting platform a few years ago on the Google superconducting quantum computer. I think Richard was actually one of those co-author on that paper. So here they also demonstrate quantum advantage using 20 entangled superconducting qubits. So we were, of course, very much inspired by this work. Okay, so what is the significance of this on this work? So this is the first photonic quantum learning advantage that we believe has been demonstrated, because the Gaussian boson sampling advantages they have been contested. Yeah, see also this work from Google. Okay, so actually what I want to say, this is what I want to say now, what I said in the first point, that this is the first proven quantum advantage experiment in optics, because I mean the Gaussian boson sampling experiment has not been proven to have demonstrated quantum advantage, but here we have a proven version of quantum advantage in optics. And what is also interesting, that it actually works, although it's noisy. It's a noisy system. I mean, we have a lot of noise in our system. As I mentioned, we're actually producing 10 dB of squeezing up front, but we only have 5 dB of squeezing at the end of the experiment, because there's a lot of loss and noise in the experiment. But despite of this, it still works. I mean, if we had 10 dB of squeezing at the very end, we could probably do the same experiment with 1,000, maybe 10,000 modes. Okay, and it's also interesting to note that it's all Gaussian, so we don't need non-Gaussianity in the experiment. And this is also very much aligned with the experiment from Google. I mean, they showed that this can be done using only Clifford operations, which is Gaussian operations in the continuous variable domain. Okay, so what is the outlook? We want to do even better. So we want to improve the squeezing, increase the squeezing. I mean, squeezing has been demonstrated up to 15 dB, but if we can just do up to 10 dB, as I already mentioned, then we can actually significantly improve the experiment and demonstrate advantages with maybe 1,000, maybe 10,000 modes. Okay, and yes, that's what I just said. Yeah, and then we also would like to implement new learning protocols. Can we come up with new channels, maybe more practical channels? I mean, the channel that we looked at here was a bit artificial because we knew that we could demonstrate a quantum advance with that type of channel. But does this correspond to a practical real-life channel? This is still not clear, but that's something that we would like to explore, and I also encourage you to explore this because I think that could really have a nice impact if we can find a practical problem where this can be used. Okay, yeah, in particular in sensing and metrology, as I also was motivating in the beginning, for example, in Raman spectroscopy, where we're doing those type of measurements, we're basically measuring the displacement of a laser beam. So, I mean, is it possible to use this technique here to radically advance the learning of molecules or maybe gravitational waves, as also mentioned here? So we still don't know about the practical relevance of the setup. I would like to thank the group and in particular also the sponsors. I should also again point out that this experimental work was really done by Cheng Hao and Roman and their colleagues in the laboratory. Thank you so much for your attention.
Okay, thank you, Ulrik. We have time. Go.
Hi, thanks for the talk. So it might be a naive question, maybe I missed something, but in the asymptotic analysis, when you're talking about, the number of samples, there's a point where you said, there's this exponential scaling, but I can kind of make it vanish by just having squeezing go to infinity or something. But, if you're going to have to spend an infinite amount of energy, that's of course not fair, right? So, can you do with kind of just a polynomial amount of energy to make that term vanish? Yeah.
No, so I mean, we cannot get rid of the exponential scaling.
No, not overall, but I mean that term specifically, right? So
yeah.
Well, there.
Yeah. Yeah, no. I mean, it only goes away in the limit of infinite energy. That's true, which of course we don't have available. So I mean, you're just reducing the exponential scaling by the amount of squeezing.
Right. So yeah. The amount of energy that you need to create the state is like e to the 2r. Is that right?
The amount of energy. Yeah. So e to the minus 2r is basically the squeezing
1 over
variance.
Energy.
Sorry?
Okay. Yeah, but that's like 1 over energy, right? So if you could say, if I take, I spend some amount of energy, you can kind of do the full accounting of, if you only spend a polynomial amount of energy, asymptotically, this term is going to vanish, but you don't need kind of an exponential amount of energy. Because then the kind of comparison's not really fair, right? If you say I'm going to spend, I don't need to take a huge number of samples because the trade-off is that now I need an exponential amount of energy. That's
yeah, okay. So what you're saying is that it depends on the beta factor here also. Yes, that's true. So this beta factor here is proportional to the number of modes.
Right.
So if this is 1 over the number of modes, then it okay.
Right. Okay. So you need the energy to kind of scale.
Yeah.
Okay.
Yeah.
Okay. Thanks.
A good point. Thanks.
Questions? Okay.
So I was wondering also, given that to have a high squeezing is difficult, could you use, for example, non-Gaussian components or something like that to improve the number of?
Yes, we definitely did not find the optimal approach here. We just used the approach that is implementable in the laboratory. but I'm pretty sure there could be other states that performs even better than the 2 mole Gaussian state. And there are also other inseparable states that performs better than the vacuum state. So that's also the line I have here. I didn't mention this, I realized. So the dashed line here is actually the lower bound for non-entangled approaches. This is the approach that we implemented classically, the vacuum state and heterodyne detection. But I mean, you can come up with many more non-Gaussian, more sophisticated dissection methods that are still non-entangled, but do better than the vacuum approach. But then this is the lower bound, so you can never go below that one. And we beat that one also. Okay.
Difference, right? In its formula. If you have like beta growing, then the R only has to scale logarithmically in beta, which I think is a mild dependence.
Okay.
The question is, how is the energy of the 2 mole squeeze state? No, is this the question, or?
I mean, the energy of the 2 mole squeeze state is just proportional to this factor here. This is the variance of the 2 mole squeeze state, and this is the energy is directly proportional to that one.
I guess. You know, we have a coffee break and we can sort out all these discussions. Yeah, let's thank Ulrik and all listeners.